Okay, in this video we're going to talk about reactance. So what is reactance? Well, reactance is sort of the equivalent to resistance. It's measured in ohms, but it's when we're dealing with capacitors and inductors. So let me just draw a capacitor and inductor, and then we'll get cracking on with it. Okay, so there we have our capacitor and our inductor. Now, when current flows down a wire, down a cable, all it sees is resistance to it flowing. If it sees resistance to it flowing, and we've got a changing signal, an alternating signal of some kind, and usually we're probably talking about some sort of audio, but we'll keep it nice and simple, and talk about fixed frequency. Then what the current will see is some resistance. So we can model both the capacitor and an inductor as an imaginary resistor, and we call this reactance. Okay, so we've got two formulas, one for the reactance of a capacitor, which is 1 over 2 pi multiplied by the frequency multiplied by our capacitor value. And then we've got then one for our reactance of our inductor, and that equals 2 pi times our frequency times our inductor value L. So C in this formula being capacitance, L in this formula being our inductor value. So the value of reactance, we'll call it pretend resistance, our model resistance, is going to be based on the frequency that we've got going through the signal frequency that we've got going through our component. I'll just draw a quick little graph to show that. So if we draw that on a graph, then as we go up in frequency, inductive reactance XL increases, whereas as we go up in frequency, XC decreases. Okay, and useful application for this, it's very, very useful to use these in audio filters and in radio receivers. So if we have a little example, if I have a 100 microfarad capacitor and I put a frequency through it of 50 hertz, then what I'm going to get out, so reactive capacitance equals 1 over 2 pi FC, so 2 pi times by our 50 hertz times by our 100 microfarad capacitor gives me 31.8 ohms. So not a lot, but it still works out okay. So we just do the same for an inductor. So you've got that. Obviously, the main thing to remember there is it's 1 over on that formula. So a quick example on this: we'll stick with 50 hertz. We've got a 512 millihenry inductor, so we can pop that into our equation. So we're popping that into our equation, and we're going to get 160 ohms, actually 161. Okay, so we don't just have a capacitor and an inductor in a circuit, we have some sort of resistance. Now the resistance might be the resistance of the inductor itself, or in the case of a capacitive circuit, it might be another capacitor. So effectively they form a potential divider, but we won't go down that rabbit hole, not today. What we want to do is to be able to work out what the combination of the real and imaginary resistance in the circuit is. Let's draw a circuit and then we can put it into context. So ultimately what we're going to be looking at is what's called impedance. Now impedance Z is equal to R squared plus, and this doesn't matter whether it's XC or XL, so we'll do XC and then we square root it. Okay, so that is equal to the square root R squared plus XL squared. So in the process of drawing the circuit, I've also just doing two quick sketch graphs to show why use Pythagoras to come up with Z. So we've got a real component resistance, and then we've got an imaginary component XC we draw coming down, and XL we draw up. So you don't need to necessarily worry too much about it, but that's where why Z is the way it is. So let's look at calculating Z for a particular circuit. So pop some values in: 100 ohms, 512 millihenries, 10 volts, AC supply, 100 hertz. So the first thing we're going to do is work out what XL is. So popping all of that into our equation, we're going to get 321.7 ohms. I suppose I could round that up to 322 if I like, but we'll leave it as it is. Okay, so if I wanted to work out what the combination of resistance in the circuit, which we call our impedance, then I can put that into our formula. So popping all of that into our formula, we work out then Z to be 336.8 ohms. So also Z also measured in ohms, because it should be, because it's the combination. It's the combination of our real and imaginary. Okay. Why is this useful? So now we know what the combination of the resistance reactance in the circuit is. So we could actually then say, what's the current flowing in the circuit? So we normally associate current with V over R. But in this case, it's V over Z. Let's pop some values in. Gives us 29.69 milliamps. Okay, fabulous. Okay, so let's just tackle this question and then we'll call it a day. So we don't know the value of C. I've got a 200 ohm resistor, 20 volt supply, and we know that 20 volts alternating signal is operating at 3 kilohertz. So what we're going to do to start with, we know the current, so let's find out what Z is from that. So Z is going to be our 20 volts divided by our 50 milliamps. So we're just popping that into our calculator. That gives us our 400 ohms. And if you remember, then that Z is equal to, it's a combination of our real and imaginary. Sorry, let me just change that to a plus sign. There we go, got a bit carried away. Okay, so we need to rearrange because we want to find XC, so we've got to rearrange it. So we can square Z and then subtract R from it. Okay, there we have it, and now we can then pop in our values. So popping those values in, we get XC as 346.4 ohms. Okay, we're almost there. So we need to find out C. So let's write down our formula for XC. So there's our formula for FC, and I like these types of formulas, so we can then see the subject of the formula. So 1 over 2 pi fxc. Popping our values in. So popping in our values, 2 pi times our 3 kilohertz signal times our 346 gives me, and obviously remembering to press our engineering friend button, gives us 153 times 10 to the minus 9 capacitance, so it's farads, so 153 nano farads. I had to think there for a second. Pressure on, I'm doing the video. That'll do for today. Hopefully that was of some use. See you again soon.